By the way,
That's
while this is starting, I was just going to mention I got a message from Dan Robertoy, who's president of ECRA, and he said that he'll be paying their yearly dues for us sheltering them from the freezing snow in the next couple days. By the way, while this is starting, I was just going to.
This is John. I was tracking the power outage, and it was almost a week from the club meeting day back in December for a week later before power was reliably back on the mountaintop.
You're saying it was off for an entire week?
Yeah. Came back on a little bit, then mostly off. It was off for 2 or 3 days after the meeting. Then it came back on briefly and then went off again. So from the December meeting to the first week after, it was more off than on.
Were the battery chargers able to take good advantage of the time it came back on?
I have no idea. I don't instrument that.
Okay.
Well, you can't charge those big batteries too fast, but I think our chargers are 30 amps, something like that.
That's not very fast for batteries that size.
Well, 30 amps times 48 volts. There is a limit to the amount of power we can draw too.
Yeah.
That's a whole lot considering.
Well,
by the way, I was going to mention one other thing. This is actually for the board, but since I'm here, we pay the storage fees down at the storage location for the club on a yearly basis, and it's due tomorrow.
Oh, okay.
It's supposed to be paid the first of the month. So I'm considering paying it myself and letting the board know that I paid it. Since I've got a couple members here, you guys see any problem with that?
I don't see any problem with that. Am I frozen? I look frozen on my side.
Yeah, you are.
Huh.
Greg, what do you? Oh no, he didn't re-up.
So yeah, like I wouldn't view that as being a problem at all. That's like standard operating funds. So yeah,
SOP.
Go ahead and do that.
All right. Yeah. Otherwise we get billed like $35 for being late.
Yeah. No, let's just get that paid. Okay. So we have the start of the meeting. It is 1931 hours. So I have the flag up behind me here. So if you want to join in the pledge allegiance to the flag of the United States of America and to the republic which stands one nation under God,
liberty and justice for all.
Oh, that's always so interesting.
My video has frozen again. Okay, so I'll just go without video today. All right, let's see. Visitor recognition. I think I recognize everybody. Is there anybody who's the first time joining us today?
You can probably say I am.
Let a bunch of people in, huh?
Yeah, I did.
Was it Mike?
Yeah, that's correct.
All right, welcome, Mike. You want to tell us where you're from and how you found us?
Heather, Kate, she's the Glark VE, and she had put out the word that you had a meeting tonight, and I figured, I'll just join and see what it's like. I've been involved with the San Diego Six Shooters, Sandark, Sandra, and the Elkhorn Amateur Radio Club, so I've been kind of busy.
Fantastic. Well, welcome. And what area are you in?
I'm in Bostonia, which is the east side of El Cajon.
Okay. I probably wouldn't hit our repeater from there, huh?
Let's see. You're on 030.
Yeah, you hit that?
No, that's ECRA, but that's the same antenna.
Okay. Well, I know I can hit that one. I have tried. I don't know if I've hit yours or not.
Okay.
Well, cool. That's on the same tower, and it's running just a shade less power.
Okay.
All right. Well, welcome.
All right. Well, thank you.
Anybody else first time? Okay. Anybody just got upgraded or just got their ticket? Okay. Announcements. I don't have very much. The scope went out yesterday, so apologies for that being pretty late, but there's a couple of things in there, including, as Mike said, the GLAARG GLARG group is doing testing. There's one coming up this coming Saturday that the last I heard, they still had some room. So if you need to do an upgrade or you have any friends or family who want to get their ticket, have them check out the Greater Los Angeles Area Amateur Radio Group. A couple of people in our group are virtual VEs for them. So there's that tie-in as well. Mark, you want to take it away with repeater tech and
comment?
Sure, go ahead, comment.
Hi,
Heather.
Hi, I'm KM6ZQB. I'm the session manager for the VE testing on Friday, and it's not posted like publicly except through my little Google site. So if they really want to be tested in that session on Friday, they're going to need to contact me or just Google CAM6ZQB ham exams and go through that little website. Because otherwise, I don't think they'll find it. This session is specifically for San Diego people. So if they go directly to GLARG or they go to Ham Study, it's not there.
Got it. Okay.
Hey, there's Joe. Hi, Joe.
Hey, Heather, I like your background. That's beautiful.
This is Balboa Park.
That's
This is
Balboa Park.
This is the one I use for testing all the time.
Ah,
Anyway, that's all I have. So back to your meeting. Sorry.
Okay, no problem. Thank you for that.
That's what this part of the meeting is for.
Yeah, interruptions. They're great. We
Well,
love them.
Announcements.
Yes, that's the other word for it. Okay.
That's a good announcement.
All right, go ahead, Mark.
Oh, well, really, I don't have a whole lot to do. I've been actually working lately. Don't tell anybody. No, it's sad, but somebody's got to do it. Anyway, as John said, the power was out. I didn't know how long. John's been tracking it. Of course, the battery bank is so massive that we really don't have any concerns unless it's out, like a couple of weeks straight. And as Phil pointed out, yes, we don't have enormous charging capabilities. On the other hand, we can't overdraw, 115 amps. So we don't want to get crazy about the power. The equipment survived. Everybody seems to be online. Still having weak problems on 14673. But I've been monitoring the weather and I'm not going up there until it clears up a little bit. Although this week we're getting Santa Ana's again, later in the early next week. So not a whole lot on this front. If anybody is interested in joining the technical team, Bernie Lafreniere is retiring. So we need things like a new host for the Echo link, somebody for the downlink to keep the radios up and running at their QTH. Otherwise, I'll end up with that one too. So anybody who wants, just send me an email, kf6wtn@everywhere.everywhere. Well, AMSET, ARRL, Gmail, pick one.
Well, speaking of hosting things, Wires X.
yes, Wires X.
Oh God, I got both of you tonight.
Mark knows me.
Yeah.
What's up?
No Wires X report for tonight. Sorry.
Okay.
All
Thank
right.
you.
Well, I'm out here with my FTM 400 and my PDN, so I could actually get in to our repeater from Palm Desert if someone would make that Wires X node come online. Hint, hint,
Or
nudge,
you
nudge.
or you could use Echolink.
Yeah, but that brings me to the 440 and yeah. Okay.
Anyway, okay.
Let's see. I don't see our membership chair. Am I blind? No. Okay. So no membership report. Hey, Kevin, I see you're here. I'm going to put you on the spot. Do you have anything coming up that you need scouting wise, or want to make any announcements or calls for, or talk about the Elmering that we were talking about earlier? Maybe Kevin's not quite here. Okay. Well, I don't have anything else. Are there any other announcements, questions, comments, etc., before we introduce the board and get on with the meeting content?
This is John. Real quick, I
Sure.
sent a notice that we got from the water board up on Palabar Mountain. Nobody responded, but I did send the PDF to the board, just making sure that it gets paid, because we certainly don't want to lose our water share up there.
Yep. I will make sure I check that and get it to the right person to get that paid. So, okay. Anything else? All right. Your board, welcome to 2021. The board of directors, the new board has been active and starting to communicate. We'll have our first official, actually, no, I guess the last board meeting of December was the first official meeting, but we'll get things kicked off next week for the board and figure out our 2021 goals and objectives. But for now, we have your repeater site and tech chair is Mark, KF6WTN, who you heard from. Scope editor is KM6CXW. I see you there. Directors Ron, AJ6FQ, and Chris, KD9LF. Membership chair Glenn, A6RR. Secretary Jim W, K2VO. I'm sorry, treasurer, and then secretary Jim C, W6TQS. Charlie, your vice president, NN3V, and I'm your president, Joe, K6JPE. All right, so tonight we are joined by Randy, KQ6RS.
Hello.
Take it away, Randy.
Okay, let me do the share screen thing with my presentation on antennas and on dipoles in particular. Do full screen. See if that works. Here we go. Okay, so I'll give a little bit of a background on just antennas in general and dipoles in particular. And dipoles are kind of that's probably about the most basic antenna type that there is. So that's kind of a good one to start. But just some general concepts of antennas. And antennas to a lot of people are kind of these mysterious things that you can't really see how they work. And so sometimes it's good to kind of give a little bit of background how they work. And I kind of remember from back in the 1970s playing with CV radios and high school student and hearing terms like antenna gain and puzzling me that how could this metal thing have gain? And then when I got my ham radio license, I knew enough to know what the length to cut an inverted V to and just looked at the SWR and trimmed it to get it to where it was resonant where I wanted. But it wasn't until later that I studied antennas and started designing them for like a day job that I understood them a lot further. So I kind of understand what it was like to, in the very early days of just being able to use them, but having no idea how they actually worked. So this will maybe help answer some of those questions for you. So we look at a little table of contents, just kind of what antennas are and some of the antenna parameters. So you can understand when you hear those. Why does a dipole resonate when it's a half wavelength long? Why that particular length? things like feed point impedance, which is important when
Yeah.
for every antenna you have to connect into them. How they interact with the ground, and so at HF frequencies, that's a significant thing. What affects their impedance? Balanced versus unbalanced. A lot of antennas are balanced, but our coax cables are unbalanced, and so that's something that has to be dealt with. I'm going to use an inverted V as an example. That's a very practical antenna to put up because it just needs one support. The ends can be tied down to something on the ground. Ways of tuning them. And then another popular antenna is the off-center fed dipole. A member from a different club wanted me to analyze his and go with an example of that. Little things like parasitic elements. That's another Yagi antennas use those. How you can have just one part of the antenna connected and other parts aren't connected, but they're there, and they interact and they change things like the radiation pattern, the impedance. So antennas, what are they? So an antenna is just a transducer between radio waves and electric current on metal conductors. So a transmitter's power becomes radiating electromagnetic waves, and on the receive side, intercepted radio waves are put to the receiver. And a real good analogy is a loudspeaker. I think we've all seen like a dynamic loudspeaker, where it's got like the magnet and the voice coil, and you connect it to an audio amplifier, and it moves the voice coil, and then that moves, creates pressure waves in the sound. Also, you can take any loudspeaker and connect it as a microphone. Sounds in the vicinity will move the voice coil of the loudspeaker, and that'll generate a voltage. So a loudspeaker, in the same way, a loudspeaker is a transducer, both as a microphone and a loudspeaker for sound waves. An antenna is a transducer for radio waves. So some of the parameters, antenna gain and radiation pattern. And let me see if I can shrink. It's kind of cutting off some of my letters. Anyways, I can't remember what was in there. So the term antenna gain, what does that actually mean? And how can a piece of wire that's not an amplifier, an amplifier takes some other source of power and creates a kind of a magnetized version of an input by drawing like a DC power source from somewhere else. But antenna is just a passive structure. There's no power source. So it can't create energy. It can, the best it can do is transmit, 100% of the power that went into it. But antennas, however, they don't radiate the power uniformly in all directions. They're somewhat unequal. So a reference point, they call it isotropic radiator, and actually is no physical thing that really exists, but it's a theoretical, what if you took the power from a transmitter and you radiated 100% of it? There was no loss, no mismatch, no power absorbed, but it sent the power off evenly in all directions. And so that's the reference point. And people like to use decibels. So a ratio of 1 is 0 dB. So you'll often see on antenna gain, they use the term dBi, and the I refers to an isotropic reference level. So for example, like a dipole antenna, typically they have very low loss, but in some directions, it'll have more power sent, and so it'll have a gain greater than 0. But of course, that comes at the expense of less power in other directions, so it'll be gain of less 0 than 0 dBi, a negative value. Other antenna parameters, the frequency range. So let's say you want to put up an antenna for, let's say, the 40-meter band. A usual reference point is the standing wave ratio of less than 2 to 1. And for a dipole, that's going to be in the ballpark of about 5% from the lowest to highest frequency. And then, as I was describing earlier, the radiation pattern is just the distribution of the radiated power in azimuth and elevation. So since we usually mount antennas on fixed objects, our reference plane's off in the earth. So elevation being relative to the horizon, from 0 on the horizon to 90 degrees, which is straight up, and azimuth, like from north, being 0 and east being 90, and so on. Antenna radiation patterns, they are exactly the same on the receive side as they are for transmit. So a direction that a transmitter would focus more, an antenna would focus more transmitter power in, is also a direction that it will gather more power. So you mentioned gain, and gain's a variable. So when they plot, you'll see like radiation pattern plots, and it's a plot of the gain relative to a specific direction, an azimuth and elevation. Something else also is the radiation pattern is really a three-dimensional shape. And usually, like with a lot of things, you have to print it on a flat piece of paper. So there's creative ways of trying to show what that looks like, either specific slices or somehow trying to show it as a spherical shape. Another term, the polarization, that's the orientation of the electric field. So for example, a vertical antenna, the electric field will be vertically oriented. It'll be parallel to the orientation of the antenna element itself. You may also hear like horizontal, like if you have a dipole that's mounted horizontally, the polarization is also in line with the conductor, but if it's horizontal relative to the Earth, that would just be called horizontally polarized. And I'm not going to go to the details. There's something called circular polarization, and that's commonly used for a lot of satellite work, like GPS signals are circularly polarized. So why is a dipole a half wavelength long? And so if you cut a dipole a certain length and you measure, the frequency range that it has the best performance on, it's going to come out to where its physical length is just about a half wavelength long. And what's happening is when you have a signal going down a wire, it propagates down that wire just about the speed of light. And when it hits the end of the wire, it's going to reflect back and off of. So at the end of a wire, you can't have any current because it has nowhere else to go. So it reflects back in phase. So it turns out that if it's a half wavelength long, reflection off of both ends, the round trip will be a full wavelength. So the phase will change by 360 degrees. So you kind of get this summation of multiple waves coming in there, and they'll kind of build up, kind of like the same way that if you have like a pendulum, like a child on a swing, there's a certain resonant frequency where if you give them a push each time, they swing for higher and higher because it's only at that frequency that you're kind of adding in phase the extra energy. So I don't know if that's a really good explanation for it, but it's where the round trip works out to where it starts summing up because the round trip's 360 degrees. So it's in phase with the new power that keeps coming in. And if you ever wondered some of the formulas for cutting a dipole to length, you may notice they're just a little shy of a half wavelength, just by a few percent. And the reason for that is there's a little bit of a fringing electric field where the wire stops. So electrically, it's slightly longer than its physical length. Here's an example. Here's the standing wave ratio. And when I say standing wave ratio, that's it's kind of a measure of the relative amount of power that reflects back off of an antenna because it doesn't perfectly match the impedance of in most cases, a 50 ohm transmission line that's feeding it. And that's a real standard way people measure with their antennas how well they match the transmitter. And if they're on frequency, typically like for a dipole, you'll cut it to where, the shorter you cut it, the higher the frequency is that it has its best match on. So in this particular case, this dipole at 67 feet long, it works pretty well on the 40 meter band. So almost exactly from 7 to 7.3 megahertz. Radiation pattern. So like I was saying before, it's kind of, there's different ways of trying to plot a three-dimensional shape on a flat surface. So in the center here, that kind of a donut plot on dipole, there's a null on along the axis of the wire, and then along the broad side is the strongest signal. So either try to plot it as like this wire grid that's three-dimensional, or the plot on the right is just a slice through the broad side, and it's hard to see what's displayed there because it's just a uniform circle. On the next plot, this is a cut in the other plane. This is like an azimuth pattern of a horizontal dipole. And you can kind of see in the grid 3D pattern on the left in red, this kind of shows this particular slice. Something else that's plot. These plots, by the way, were generated with the EasyNet program, which is kind of a handy program for modeling antennas. but that pink line is it shows what the current flowing on the wire is. So it's a maximum in the center, and it's zero at the ends, which makes sense. At the end of a wire, there's nowhere else for current to go. It has to go to zero. A big thing that comes into play at HF frequencies is the effects of the ground, because it's not practical to get huge distances above the ground. So for example, at this 40-meter antenna up at 68 feet above the ground, that's only a half wavelength above the ground. And what happens is there's a reflection off of the ground, and that's called, kind of creates like an image antenna. So in the same height the actual physical antenna is above the ground, there's this image that sits below the ground. And off in the distance, the signals from both the main antenna and the reflection will combine. And at some elevation angles, they'll combine in phase, and at others, they'll cancel. And so that the radiation pattern on the right shows for a 40-meter antenna that's a half wave above the ground. You get a peak at 30 degrees elevation. And in the next page, I kind of modeled what's really going on here. So I took a dipole, and when they talk about antennas in free space, they mean it's away from the ground. But here is actually, I took the same dipole that's a half wave above ground, and then there's no ground in this model, but at the same distance, a half wave below the ground level, so in other words, one wavelength away from it, I drew another identical dipole, but I feed it with 180 degrees out of phase and 80% of the amplitude. And you can see on the radiation pattern for the part of it that's above the ground, it looks very similar. And the question might come is, well, why is the peak at 30 degrees? What's going on with that? And it's just ends up being simple trigonometry. At a 30-degree angle, the signals from both antennas are going to be in phase. The reflection off the ground is at 180-degree phase from the original signal. And at a 30-degree tilt, if there's a one wavelength difference, that adds a half wavelength path difference. So the reflection being 180 degrees plus another 180 degrees of having to go an extra half wavelength now makes them in phase, which is why they will peak up at that 30-degree elevation angle. That kind of also tells you why the higher the antenna is off the ground, the lower elevation angle, you get peak power, which normally is what you want for DX communication. You want most of your power at a relatively low elevation angle, and a high antenna will get you more of that. Here's like a more practical case, getting 34 feet off the ground. At a quarter wavelength, the peak is going to be straight overhead, because now there's a half wavelength difference between the antenna and its reflection. And since the reflection is 180 degrees out of phase, it's straight up at 90 degrees that they're in phase. So that's kind of how reflections off the ground will affect the radiation pattern. And then here's kind of a more extreme case. It's only, if you only get up 17 feet or an eighth of a wavelength, it has a similar radiation pattern, but the gain values start dropping off. So it doesn't mean it doesn't work. It just doesn't work as well as a higher antenna. Something else to keep in mind is mentioned balanced antennas versus unbalanced feed lines. For at the frequencies we work at, the skin effect is a real the current will only flow on maybe not even a thousandth of an inch of thickness of the metal. So on a coax cable, you've got the interconductor, so the current pretty much only flows on the outer surface of the interconductor. And it also, on the coax cable, it only flows on the inner surface of the outer conductor. And there's no connection between through the outer conductor of the coax or the shield, except where the shield stops. So right at the point where you connect your antenna and your shield stops, if you look at this picture here, just think of where you've cut off the shield as that's the one point you've connected together the inner and outer surfaces of the outer conductor. So if you just connect a coax cable directly to a dipole antenna, all the current flowing in the center conductor is only connected to one thing. It's connected to one arm of your dipole. But the current that flowed on the inner surface of the outer conductor is connected to two sources of metal, one being the one part of the dipole, the other being flowing back down its outer surface. On the simulation on the left, wire one's just in the model where you have to feed it. That would just represent right at the end of the coax. Wire 2 is the side that's also connected to the shield. And wire 4 is coming down the shield, and wire 3 is the one connected to the center conductor. And you can kind of see from the pink graphs that there's a lot more current flowing on wire 3, which is from the center conductor. But the current that was flowing on the outer conductor is kind of shared between the one arm of the dipole, which is wire 2, and running back down the shield. And where there's current is where there's radiation. So in this case, you're kind of getting the undesirable effects of having signal radiating off of the shield, plus you're getting RF back in your shack, and it'll affect the SWR. So it's generally an undesirable thing. So people talk about making some kind of a balanced or balanced to unbalanced transformer. And a simple practical way of doing that is just putting ferrite cores over the outside of the coax. And what those will do is they'll have no effect on the signal inside the coax, but just the signal that tries to run down the outside. And for these particular, this is a very common type 31 ferrite core, and it's made where it'll fit over like an RG8 size coax. It's about a 4/10 of an inch inside diameter. And they make both the solid core version and the ones that clamp over. The clamp over ones are useful for cables that already exist, or it's got a connector on it, you can't run it through. And in this particular example, at 7 megahertz, each one adds about 80 ohms resistive and about 58 ohms inductive. So if you stack 6 of these together, you've now added about 500 ohms of impedance. And so that's now in parallel with the roughly 36 ohms impedance that the one arm of the dipole has. So what you've done is, this kind of models what happens if you've added 500 ohms of impedance to the line that represents the outside of the coax. So very little now will flow down the coax. It's almost entirely flowing on the dipole. So this is one way of creating a balanced to unbalanced transition from coax to a dipole. You didn't do it with a transformer that's like a balanced to unbalanced. You just created a huge impedance for the path you didn't want. So ferrites are pretty handy at HF frequencies. Excuse me. Another antenna that's, I mentioned the practical antennas like an inverted V. It only needs one support. So like in my house, I've got a mast on the roof, and I've got inverted Vs tied to it for several bands, like 80, 40, and 30 meters. And here's just a model of one up where the apex is up at 34 feet. Another advantage of inverted Vs, but besides being a dipole, where a dipole needs 2 supports, is sloping the wires down lowers the impedance just about to 50 ohms. So they tend to have a really good match for 50 ohm coax. Another thing, when you look at the normally radiation pattern of a dipole in free space, you've probably heard, well, they radiate off the broadside, but what about the ends? Do I get no signal at all? And it turns out in the presence of the ground, you actually do get a signal. That the plot on the right might be a little hard to see. It shows total power, which is black, and it shows the component that's horizontally polarized, which is a blue, and that peaks broadside to the wire. But off of the ends, there's a vertically polarized component. So you actually get a fair amount of power kind of in all azimuth directions. So it's a real kind of handy, easy antenna for especially the bands that are at 40 meters and 80 meters. For tuning, can't see all some of the stuff on the windows blocking the text here, but so I'm just kind of going to what I remember. But usually for cutting like a dipole inverted V, the easy thing, it's a lot easier to cut something shorter than to splice something to make it longer. And I had a case where I raised my mast up 10 feet. It used to be at 35 feet. Now it's 45 feet. And that ended up shifting up the frequency of some of my inverted Vs a little higher. So I needed a longer wire. So rather than splice in some wire, I just left it connected to the insulator as they were, and just tacked on, soldered on a little bit of an extension. And so there's no reason that the end of your antenna has to be where the insulator is. You can have a little extension hanging off of it. And I thought that was kind of a practical way. Something else too, when you tune antennas, you can have, like something I did once, I've got an 80, 40, and 30 meter inverted Vs all fed from the same coax. And that works really well for each of the bands. And you don't have to really have them spaced out. You don't have to space them out equally like around the circle and azimuth. You just need a little bit of separation between them. But for tuning it, always first trim the low frequencies first. The reason being, when you get to a dipole is resonant, or inverted V for that matter too, is resonant when it's a half wavelength long. It has another resonance every time the length is an odd multiple of a half wavelength. So at 3 times the frequency and 5 times the frequency, it'll also be resonant again. But an antenna that's significantly shorter than a half wavelength is going to have an extremely high impedance, and it won't affect anything else it's connected to. So the reason you want to first trim the longest wires at the lowest frequencies is because then once you've got them working on the frequencies you want, you're not going to change them. Whereas if you first trimmed your shortest wires at the highest frequencies and then went to, there might be some current drawn at the highest frequencies from the longer wires. So to not have to go back and retune wires multiple times, as long as you do the longest wires first and then work your way up in frequency, you only have to go through it once. Here's an example. This was an off-center fed dipole that Bud AE6BH asked me to model an EasyNet, and he feeds it with a 4-to-1 Balun. And so you may have heard of 4-to-1 Baluns and 9-to-1 Baluns. Just a straight dipole that's a half wavelength long, and if there was no ground involved, is 72 ohms. If you can feed dipoles off center, and what happens as you start going off center, the impedance rises, and by the time you get out to the very end, there's some end-fed type antennas like J-poles and stuff. That's close to a 2,000 ohm impedance. So these Baluns, they've got kind of these 4-to-1, 9-to-1 Baluns, they've got a transformer ratio in there. So it turns out that 200 ohms is kind of closer to the impedance you actually see, at about the, 1/3, 2/3 point along a off-center fed dipole. And here I ran an analysis over a really wide frequency range, all the way, from 80 meters, from 3 to 30 megahertz. And you'll hit these multiple resonant points, like it's a half wavelength long at 3.5 megahertz, and then it's a full wavelength long at 7, and kind of so on. Interesting thing to look at is the currents flowing on the wires and the radiation pattern. So where it's a half wavelength long, you just get the highest current in the center, and it drops off at the ends, and you get kind of a normal dipole pattern. But at higher frequencies, you'll actually get these peaks and nulls in the current. And what it doesn't show in that plot, that's just showing the amplitude of the current, but they actually change polarity. So let's say the hump most on the left is, let's say, has one polarity, the next one is the opposite, and then the original polarity and the opposite again. So every element of the antenna where that current's flowing on is radiating some signal. And what that means is, in different directions around the antenna, there's a different amount of distance to the different parts of the antenna. And so that'll change the relative phase that all the radiation off the different parts of the antenna arrive at in different directions. And that's why on this radiation pattern, it's kind of this big lumpy cloverleaf thing. In the directions where it's highest is where the kind of vector sum of all these parts have close to come to a peak. And where the nulls are is where they close to cancel each other out. Passive elements, the Yagi antenna is an example of where that's taken advantage of. In this case, the driven element, which is, say there's a center, there's a driven, there's a reflector behind it, which is a little bit longer than a half wavelength, and there's a director, which is in front of it, which is a little shorter. So what happens is, as the length of an antenna element changes, it's going to affect the phase of the current. If you're above or below resonance, like a dipole that's shorter than resonance will look a little capacitive. If it's longer, look a little inductive, and that'll change the relative phase of the current. So for something like a Yagi, what they do is, depending on the spacing between the elements and the length of the elements, that affects the relative phase flowing on each of the elements. And and even though only the center element actually is connected to the current that's induced on the other element, since there's current on the elements, that will now be another radiator. And so they're designed such that in the forward direction, the radiated signals add up in phase, and in the reverse direction, they cancel each other out. And so for that reason, you'll get a gain increase in the forward direction, and you get a big a null. You know, they talk about the front to back ratio in the back. And that's a way of altering a radiation pattern without actually having to physically connect to every part of the antenna that's doing the radiating. And I believe that was the last slide. It was. Okay. So any questions on it? Let me stop sharing. Everyone's quiet. I hope you heard the whole thing.
Well, I did. I learned an awful lot, because in the old days I had a 90-foot dipole sloper, and it went from the top of my air conditioning unit on my house out to the farthest edge of the fence, which was still 6 feet from the ground, so nobody would do that sucker. But I certainly couldn't do everything you're talking about there. So I'm not technically oriented, but I certainly learned a lot.
Okay. Yeah, I mean, antennas are kind of a fascinating subject, and by some
Something like
weird twist of fate, I ended up
something nice.
spending my most of career designing mostly higher frequency antennas for like military and like cell phones and concealed military projects.
Hey, Randy.
Yeah. Hey, Mike.
So hi. One of the things that I noticed, I think I remember this correctly, is the closer you got it to ground, the lower the minimum SWR. What's that about?
The lower cut. Well, so, and it actually, so as you have like a inverted V or dipole move across the ground, the impedance will actually go through, it'll go high and low and high and low, depending on, there's some coupling to the reflected signal off the ground, and depending on the phase that arrives at the antenna, it'll change the impedance. And so how high and or below, above or below that gets to the 50 ohm point, that'll change the SWR. But there's, so just in free space, the dipole is 72 ohms. And as it goes above and below 50, I've played around with looking like on the simulations as you bring it lower and lower. Eventually when it gets really low, the impedance gets really low, but there are actually some heights that the impedance rises above it. And so what you'll notice is when you do your SWR plot and you're going for where the resonant frequency is, it doesn't hit a perfect 1-to-1. It kind of hits some minimum and then it rises up again. And that's kind of how the impedance is affected by the interaction with the ground. It's kind of like you've got another antenna that's almost the same power, but with the opposite phase. And the way it couples into the actual physical antenna is going to raise or lower the impedance. Now, did that help? Engineering is, retired engineering is not my problem. I should say that too.
Hey, Randy, I have a question.
Yeah.
I'm thinking of putting up an off-center fed dipole.
Okay.
And could that be fed with a window line instead of hanging a transformer up there?
The thing with the window line is, that's usually in the order of 400 ohms. And so depending on the length it is, I guess if you feed it off center, well, I think depending on how far off center it's fed and the length of the window line, you might get some really funky, crazy impedances. And at some point you're gonna have to convert from the window line back to a balanced line. And that might be with an antenna tuner.
Yeah, I've got a balanced tuner. So I'm just thinking, they always talk about you need to put a Balun right at the feed point if your antenna is even on dipole if it's unbalanced. So
okay.
Would I need a Balun up there, or?
So not until not at the window line you wouldn't, but at where the window, well, and depending on what kind of Balun or transformer you have between the window line and your 50 ohm coax, there may be some that actually do the balanced to unbalanced conversion, internally.
Yeah. My tuner's actually has a balanced output on it, so I just
Oh, okay.
run
So
the window straight to that.
yeah, so that'll take care of the balanced to unbalanced transition. And I don't have much experience with. I've never built an off-center Fred dipole, but I've just had a couple of people ask me about them, and I've thrown them into that EasyNet program. But I don't have any of that kind of been playing around with it myself. Gut feel for them.
Okay, cool. So that'll be my next antenna project.
Okay.
Comment, Randy.
Yeah.
So I've done that with open line, and the problem with it is without the Balun, you can't put a choke on it. So you do get the RF coming down the feed line, and it's coming right down into your shack if you have your tuner in the shack. And tuners and many tuners that I've seen, unless you get up to the more expensive ones, are not really balanced. They have a pole, a ground, two things that say balanced, but one of them's grounded and one of them's into the center connector. So they're not really balanced. But yeah, I have a couple of tuners that are exactly that way. The wire goes from the end of the tuner to the coax, and it also goes up to a binding post. So you got to be careful what kind of internal circuitry you have on the tuner.
Yeah, I think you probably
internally, my tuner's just got a coil that's coupled to the tune circuit inside, so it's not really connected to ground anywhere on the output side.
Well, but normally you have a pi tuner, which is a capacitor on the input, a capacitor on the output, and a coil in between, right?
There's an output coil, and then interwound with that coil, not attached to it, is the output to the.
So it's got a coupled output to an output coupling coil.
Yeah, right.
Okay, well that's probably balanced then.
Yeah.
And it'd probably be good if you have that conversion, instead of running the twin lead all the way back to your shack, you kind of have the tuner at some point on the ground. But unless that offset fender dipole's up really high, I think it'd be just safer just running like a 4-to-1 Balun to it and not worrying about what the tuner's doing. Although there's a crazy example, there's a guy, and he's on the air a lot on like 20-meter voice. I know Mike Tango Whiskey's John's is in Vancouver Island, and he put it's some 960 feet of wire up in these pine trees, up 100 feet off the ground. He made this multi-wavelength horizontal loop, and he built this ladder line to feed it. And the ladder line, it's like 2 or 3 feet between the arms. It looks like a picket fence if it's just sitting on the ground. And he has this tuner down at the ground. So there's a lot of reflected energy on it, but it's very low loss. But he does the tuning work where that ladder line, the 100 feet below the antenna down at ground level, and then he comes into his house with a 50 ohm coax. But that's an example of where ladder lines really used. But other than that, I don't really have a lot of experience with it, or pretty much no experience with it.
Okay, thanks.
Okay. Any other questions? And I guess if someone wants a copy of these slides, I could just email them to you. If anyone thinks they're going to be of any use.
When you were talking about having to make antennas just a little bit longer, you might want to explain velocity of propagation, V sub P.
Oh, okay. So
and why things don't travel quite at the speed of light.
So for well, especially like in a coax cable, you've got what's supporting the center conductor is is like a usually Teflon based type dielectric, and so the speed that something propagates in the transmission line is dependent on the the permittivity and the permeability of the material it's going through. And in vacuum, the relative permittivity and permeability is 1 if vacuum's your reference point. So with a dielectric and a coax, the velocity of propagation might be something like 80% slower. The thing with an antenna, though, I don't think it's a velocity of propagation thing. I think it's more because the only dielectric around it is if it's just straight wire, is just the air, which is essentially the same as vacuum. But I think it's the fringing effect off the end that causes the physical length to be maybe 1% or 2 or 3 shorter than actual wavelength. Everyone got quiet.
This is John, WB6IQS.
Yeah.
Whenever electric radiated fields travel in a medium like a conductor, they're always a little slower. They're never at the full speed of light. So I always use 95%. But it's especially noticeable, of course, with velocity of propagation when you have your coax cables, because you can get down to 66% on some of the cables, or even in lower, I gather.
So it goes with, so for cable, Teflon has a dielectric constant of, I think it's like 2.1. So for cables that have solid Teflon dielectric, it go with the square root of 2.1. Most coaxes for lower loss, it's kind of like an air, they've kind of foamed the Teflon. So there's it's like a mix of Teflon and air. And of course, air is close to 1. And so you'll get, instead of velocity, I think if it's, it'd be in the 60 some or 60%. If you take 1 over the square root of 2.1, it's, I think, in the high 60% range. But a lot of coax velocity propagation is closer to 80%. And the reason they do that is for coax cable, most of the loss at HF is a resistive loss on the conductor. And for 50 ohm coax, there's a ratio between the outer and inner conductor, and that's also dependent on the dielectric constant. So the lower you can make the dielectric constant, the larger you can make the inner diameter of the coax, which will lower the loss. Pretty much in coax, the only job the dielectric is just a mechanical way of just keeping the center conductor close to the center. So, I mean, that's different than velocity propagation on an antenna, but that's a little bit of what's going on inside a cable.
We have a large diameter hard line up on top of Mount Palomar, and the foam dielectric looks almost like some kind of a sponge, very lightweight sponge material. And it's got a very low bending radius where you cannot bend it at any sharp angles. And they have all kinds of tables to tell you how far you can do it. But some of the hard line we have on the mountaintop is almost 1 inch in diameter. And I believe it's like 85% velocity factor.
Okay, yeah, that makes sense. Is they just want to get the least amount of dielectric in there, and to get the loss. So the large size is to get the loss down. The bigger it is, the lower the current density is. You know, you get the same total current based on the power and the impedance. But if you can have the conductors fatter, especially the inner conductor is in the ballpark of a third of the size of the outer conductor. So the primary loss is the outer surface of the inner conductor. So anything you can do to make that larger. And so if you're limited to a certain overall outside dimension, anything you do to get the inside conductor diameter larger will lower the loss. And the only way you can do that is by reducing the dielectric constant. Like you said, you just take kind of a Teflon and you make it foam like sponge. You're electrically getting it closer to air, but you've got enough material still there to mechanically support the center conductor. And kind of like you pointed out, there's these restrictions to how tight you can bend it, because that's going to, near where you bend it, it's going to kind of be pushing the center conductor a little off center.
The connectors are hideously expensive for that cable, but if you're trying to pump 250 watts of video at 2.4 gigahertz up a tower, that's really the only way to go.
Yeah, so the loss is greater with frequency, and of course it's greater with distance. So depending on how high your frequency is and how far you got to get it, is going to dictate how large or how the dB per 100 foot number you're going to need for the type of cable you need. And that usually means bigger and more expensive, to get that number down.
I just, throwing some observations out. practical RF. It's always a matter of money and invested money versus time and trouble to install it. Your cable TV stuff, you can get away with almost anything, but lately stuff you have to use the RG6 cable now for stuff, because in a lot of cases the cable TV people are pumping signals out there close to 1 gigahertz.
Okay, yeah, the higher than they used to. So yeah, the loss per distance will be greater.
I'll tell you what, if you're interested, I grabbed a picture of what a 3-inch heliax looks like.
Oh yeah, so you can kind of see the for the dielect, or for the support of the center conductor, they've just spiraled this, you know, that's getting pretty close to air. And it'd actually be interesting, what did they give what the velocity of propagation is?
You know, they probably do somewhere. Let me.
I can imagine it's getting really close to 1.
Yeah, let me try and get rid of some of the Zoom stuff that's in the way.
Looks like you could bend that too.
Oh, they're 93%.
Yeah, so it's 0.93, which is, quite frankly, is really fast.
Yeah, well, I mean, if it were just air, it'd be 1.
Yeah,
but
well, close. I remember, unfortunately, all those classes I had to take in electromagnetic field theory, where they were always making you use like 1.001 or something like that. Otherwise, the teacher would think that you were cheating and using a vacuum.
Oh, but the main motivation is it's I think I remember, like, it was the impedance of coax. It's 60 times the natural log of the outer diameter over the inner diameter, and that would be, you know, in a vacuum, and then that would be reduced by the square root of the dielectric constant. But the actual dielectric constant, if you've got a mix of things, in this case, you've probably got this Teflon spirally spiky thing with these gaps in it and air. So you've got kind of this weighted average of the air in there and the bits of Teflon. You know, Teflon's dielectric about 2.1 and air is 1.0. So, you know, it's mostly air. But because of that formula, that changes the inner to outer diameter ratio, and the less dielectric, the larger the inner diameter, up to the point where it's just air in there, and then the loss goes down.
This is John, WB6IQS again. I was told, I don't know, you may have a different opinion, but I was told that any electric field going through a real conductor is always slowed. It's only when the electric field is going through a vacuum in space that it's at 100% of the speed of light. But any electric field going down a copper wire, for an example, is slowed just by the nature of going through the copper wire.
I think that's probably almost infinitesimal. I know if you had just pure, if you had no dielectric at all, I mean, the difference between vacuum and air is there's almost none. I mean, it's a very tiny, but I think it's like out to the 3rd decimal place kind of difference. You know, maybe vacuum has a dielectric constant of, you know, 1.000, and air is, you know, 1.002 or something. It's, you know, it's essentially, you know, equal to the same as a vacuum. I mean, unless one wants to just argue, you know, some theoretical difference that, yeah, it's not exactly the same, but from a practical standpoint, it's almost exactly the same.
Yeah. Whenever
I agree with you, but sometimes you have a professor that you know, is a perfectionist, and unfortunately we did.
Yeah, and he never actually had to build anything, so he didn't know what really.
You know, I don't think he ever did. By the way, here's a nice shot of it. Since most people are used to dealing with, you know, like TMS 400 and things, here's a shot of some of the different types of heliacs. The one that we're using on the hill is a lot like this one right here, if you can see the mouse pointer.
Okay, yeah,
It's not a solid core. It's a hollow core, but not corrugated.
okay.
And then foam, and then of course a corrugated external core, and a shield. And John, ours is what, 5/8, I think, is most of what we run is 5/8.
It was mostly 1/2 inch LDF 450, and we have some 7/8 inch cable up there for some of the
The 1.2
like
stuff.
microwave gear.
Yeah, which looks mostly like this or like this.
The 6-meter repeater I just got on regular old RG213 or RG214 because the losses at 50 megahertz are almost meaningless.
And of course, one of the things that you mentioned during your lecture is that when you get up into RF, all the energy travels over the skin. So you'll notice that the center cores of these are all hollow because you don't need the mass.
Right, yeah, and it's probably more bendable. But yeah, it's interesting. I'm just looking at how they've tried to get the dielectric down to almost nothing. I mean, they got the teeniest amount left just to keep that thing from falling out of the center position.
And I should tell you a lot of this stuff. I don't know if you've been dealing much with Anders Heliax, but most of this stuff, even the little stuff that we use like this, the minimum bend radius is 3 feet.
Yeah.
So the bottom of our tower has these nice, big, wide curves where it's laying on the ground, and then it transitions to get, we just use tie wraps to tie it onto one of the arms, one of the verticals on the tower.
Yeah, I can see with so little support of the center conductor, why it'd have to be a very gentle. So what frequency did you just go to waveguide, not coax at all?
We're not using any waveguide here at all. We're using this.
Okay.
For everything. But we only go up, mostly we're running 2-meter 440.
Okay.
We've got some 1.2, although it's not currently active. But that's it. So that's why stuff like this works out well for us. And we have other problems on the mountain, like lightning strikes. And the nice thing is that you could terminate this stuff. The building that we have is actually an old AT&T switching building.
Okay.
And it has some really nice pass-throughs and all sorts of, the building itself is a Faraday cage.
Okay.
So we've got some really nice pass-throughs that go from outside the building with an in connector on one side and the other, and a lightning arrestor in the center that takes everything to ground. And then good old Stan Rohr, who did this stuff for us originally, has got this thing grounded 6 ways to Sunday, not with little bitty wires, like you said, because a thin little wire won't carry the RF. So we're running multiple 6-inch wide copper strips.
Wow.
And the copper strips ground everything, building to building, building to multiple grounding, 8-foot grounding posts, grounding the tower. We don't get hit real often, but then we haven't gotten knocked off the air when we do get hit.
Yeah, at home I haven't worried about lightning at all. I think it's just because I'm, not on top of a mountain and don't worry about it, but it'd probably be bad if I did.
Yeah, I do live on top of a mountain. And it gets a little eerie when you're watching it and it's hitting all around you. You just, it's what we refer to up here as an increased pucker factor.
Yeah. Yeah, I think you had some people checking out. I guess they're interesting.
Yeah. Well, the meeting is a little bit shorter than we run a lot of times. But it's really interesting discussing not only the theory of antennas, but how we get signals up to them. And I was just, most people are used to saying coax because you know, they've got their equipment at home.
But yeah,
I
that's
thought
interesting. You know, these extreme cases of, you know, high frequencies, long lengths, or really high power levels, and how you end up using this real exotic stuff, you know, for usually more commercial type applications. And I know some high power ones, I think they pressurize them. I think the dielectric,
or they run a vacuum. They'll run a vacuum. They'll run dry nitrogen inside of them.
Okay.
So yeah, especially things like this in the middle there.
Okay.
They'll run dry nitrogen inside of them.
Okay.
Try and keep a consistent signal. But you will notice in the case of this one, they're saying, I don't know how well you can read this. They're saying 3 inches.
That's pretty clear.
3 inches. But then if you go back and you look down at the bottom somewhere, they talk about the maximum power that you can run through this thing. And it's like, there it is. No, not to exceed 640 kilowatts.
I guess it would, I guess depending on the frequency range.
Oh yeah. I'm sure it derates as you get up to higher frequencies.
Yeah, and then there's, I guess, the power. I guess some voltage or some voltage will arc over it at some power level to overheat.
Yeah, I should tell everyone our repeaters are running 25 watts.
Yeah, you could use any coax for that.
Pretty much.
Well, we're not limited. You know, we don't care as much about the power output.
You got the losses.
You know, we've got nice 4-bay and 8-bay antennas up there, which you didn't go into. Collinears.
Oh, so these will give you like a higher gain they kind of, it's a focused elevation pattern.
It takes your donut and makes it into a ring.
Right.
You've got less on the top and the bottom, but more gain, so to speak, heading outward. And so we're using 4-bay and 8-bays with reflectors behind them because we really don't need to transmit into Palomar Mountain. We really want all of our energy to radiate down towards San Diego.
Okay.
So we're on the top of the mountain, radiating, but we can see to the south perfectly, and to the north, not really at all. There's a guy in a camper back there. That's pretty much it. And we don't need to, you know, we don't need to keep his microwave running at night for him.
Yeah.
So we radiate all of our energy down towards San Diego with our 4 bays on 2 meter and 8 bays on 70 centimeters, running heliacs like this up on the top.
Okay.
You like that price? Oh, I like that. Call for availability.
Was that like that?
Probably cost per foot, by the way.
Yeah.
Ouch.
Yeah.
But you can finance up to 250,000.
Yeah.
Yeah. Yeah, you can finance up to 250K.
Well, probably a lot of this is, you know, like commercial radio station markets. You know,
Oh yeah.
Yeah. Now this one kind of got me.
Elliptical waveguide.
Yeah.
Oh.
I'm used to square waveguide. I'm old.
What
rectangular.
So what frequency is that for? That
I have no idea.
They only $7,400. That's probably for like a big roll of it.
Well, what's the
1,000-foot reel?
Well, what's the inside dimensions? That'll tell you the minimum. That'll tell you the cutoff frequency. Oh, here you go. 10.2 to 11.7. So it's XPU.
You're probably in the ballpark of an inch inside diameter-ish.
Something like that. $7 a foot. Hey, there's no center conductor. You got gypped on this stuff.
Yeah, that's what
what a ripoff.
Yeah.
Look, Doug M wants into our meeting. Yeah, there you got a ripoff. There's well, you know, you're always talking about the thinner and lighter that center conductor is.
Yeah.
So there you got the ultimate. It's so thin you can't even see it.
Well, so I mean, with waveguide, all the current is just flowing down, the outside surface, or actually the inside of the one surface. So waveguide tends to have very low loss because the current's distributed over a large area.
Right.
Yeah.
Yeah. You remember the additional. Remember the different modes. To see this one has a TE 11 mode cutoff. Coaxial cable, as I recall, is TEM, right? Transverse electrical and magnetic. It goes transverse to the direction of propagation. With waveguide, you can't do that because there's no conductor down the center.
Yeah, there's like TE01 and
yeah.
And actually coax cables, if it's depending, you can get waveguide modes in coax cables, which is undesirable. But
you sure can. Yeah, if the frequency is high enough.
Right, for the
but
size.
only coax can go to 0 because only TEM can go to 0.
Exactly. Yeah. But that's.
What is it, honey?
What was that question?
Oh. When I teach classes, Randy, I like to tickle the students' brains. I say, why do we have to spend so much money and effort, getting a signal only a few feet, and then it goes out in the air where it doesn't need any help at all, and it goes for many miles? Why is that? I get them to think about that for a while. And I also ask questions like, let's say you got a buddy in Germany and you want to talk to him, and we give you the best possible coax you can buy, directly connected, connector to connector. Would it work?
Oh, interesting question. Huh.
Well, would it?
Maybe not.
No.
Versus just over the air.
Yeah. Well, it's a difference between exponential and inverse square.
Oh, true. Yeah. Because you're gonna, let's say if you lose 10 dB every 1,000 feet, then it's like every 1,000 feet you're down to 1/10 of the previous 1,000 feet. Interesting. Yeah. Never thought of buying like the coax that long, but.
Well, do the numbers sometime.
The other one that's a real interesting one to think about, and I think it's the one I like to use the example of why radio is possible, is the ratio of the amount of power you need to receive, versus transmit power. And I think I did it for like cell phones. I think the sensitivity is something like what was it, like 100 and minus 120 dBm versus 20 watts being transmitted. And I worked it out, and it was, I have to recheck my numbers, but it was something like the ratio of, if you assume a backyard swimming pool holds about 13,000 gallons, it was something like the ratio of one drop to 4,000 swimming pools, in terms of how little, like you could take that one drop and spread it over 4,000 swimming pools, and there'll still be enough for it to be detected. How little you need of what was sent out to be able to get it.
Well, another way of saying that is a Boltzmann's constant is small.
Yeah, right. Yeah, the world's pretty quiet, which is, yeah.
Right. Or our temperature anyway. K, the value of K, 1.38 times, what is it, 10 to the minus 23rd? I used to know that number.
I just know it at room temperature minus 174 dBm per hertz.
Yeah, right. That's the reason, right? Because if it weren't for that, you could just add gain as much as you wanted, right?
Right, yeah. So, yeah, interesting stuff.
But no, the answer with, even if you had the best possible grade of heliax, you'd have to nuke the coast and you would still not be heard on the other end. The attenuation is that great without repeaters, which makes the accomplishment of fiber optics even more impressive.
Well, that's
look
true.
at how transparent they are.
That's true.
Mm-hmm.
Well, I guess what we should ask is, for those remaining, are there any other questions?
This is John again, WB6IQS.
Sure.
I've run through some calculations, and I just was curious what your point is about SETI, the search for extraterrestrial RF signals, because everything I've ever run through my limited EM calculations says that there's no possible way they're going to be out there light years away and transmitting any kind of RF power that anything on Earth could have detected, short of us setting up some kind of dipole array that goes from one end of the orbit of the Earth to the other end of the orbit of the Earth.
Well, it depends on what you're looking for. If you're just looking for carriers, you know exactly where they are. You know, and you had an Arecibo, which we don't anymore, to receive it. You know, you can just barely detect them. But you know, as radio has progressed, you know, we're getting away from carriers. We don't transmit lots of power in carriers anymore, right? So it was only a brief time in which it was even possible for us to be detected that way. But it used to be that UHF TV carriers are about the brightest radiations of the Earth. I did that number once.
But I mean, like radar pulses, if I was was I 4 or 5 light years away, could I detect radar pulses?
Well, it's not pulses. It's not the peak power. It's the average power. It's the total power. So, you know, what are the biggest transmitters we had? And there were probably UHF TV transmitters on, you know, the quietest parts of the bands. So, yeah, I mean, work it out, you know, for NTSC with a flat pancake antenna that's firing at the horizon. You know, you might just barely be able to detect it. I had to run the numbers again, but you know, that's the kind of signal you might just barely detect at interstellar distances.
All right.
But how long did NTSC last as a technology, right? We were only doing that for, you know, several tens of years.
Yeah, out of the history of humans on Earth, yeah.
And which is already pretty short.
Yeah, so it's the probability just seems like forget it.
Yeah. Well, you've heard my corollary to Clark's law, right?
No.
Clark's law: any sufficiently advanced technology is indistinguishable from magic. Well, Carnes' corollary to Clark's law is that any sufficiently advanced communication signal is indistinguishable from noise. Which is actually true. I mean, look at Shannon. It is actually true.
Interesting.
Yeah, think about it.
Yeah, and then it'd be drowned out by, you know, all the.
So we're being bombarded by signals everywhere. We just think they're noise right now.
Well, it's true, the whole background radiation of.
Yeah.
That would.
Well, we think we understand the mechanisms, you know, and they're quantum mechanical and don't carry any information. At least so we think.
That's true. It's encrypted.
Yeah. I still don't think we're ever going to.
It's probably all done with entangled particles, so we can't drop in.
Yeah,
on it.
well,
can't drop in on it anyway.
Yeah. Oh God, that is so sad. That picture.
Yeah, doesn't that literally bring tears?
Oh
to
God,
your eyes?
yes. You know, I actually used that dish once. I've never been there. I regret never having been there, just like I regret never having been inside Notre Dame. But I used that dish once. I got the signals from ISE-3 back in 2014 when we were trying to rescue that satellite. They would ship either raw signals and I would decode them. And what was ridiculous is that we were getting signal. I was getting signal error ratios like 30 dB when this thing was still many light minutes away. It was ridiculously strong. Oh God, that is so bad.
Here, we'll put this one over it.
Yeah, that looks.
I like that pic. I like that picture much better. I was thinking when they just had, you know, that one little bit of damage, I kept saying, "Oh, they're going to fix it. They're going to fix it."
Yeah. But once you saw the situation,
and then
you know, you realized,
they lost that big support cable right there, and the whole thing went crashing down.
Yeah, I mean, they had a drone flying, looking at the damage as it broke. Yeah. Well, the steel had apparently lost like 50% of its strength. When they realized that, they realized that the thing was about to collapse at any moment. You know, I'm not sure technologically it makes sense to rebuild something like Arecibo anymore. Large phased arrays seem to make more sense.
Well, I hate to agree with you, but
yeah, I know I have strong, you know, sentimental attachment to this thing, but science doesn't run on sentiment, so well, it doesn't.
They did receive some sort of money after the collapse, and I am looking for the article, but they received money. I don't know if it was to try to do something at the site and fix it or what it was for, but it was quite a bit of money.
Yeah, I think it would probably take a lot to actually rebuild it the way it was. And then you have to ask the question, would that money be better spent some other way? Like on a large phased array.
A nice, really flat desert away from everywhere and build a bunch of receivers.
Yeah. I mean, you know, as nice as
of a
this was,
reasonable size.
remember, this thing was never built to do radio astronomy, right? It was originally built to do ionospheric radar experiments. That's why its point is straight up. It can only see within about 20 degrees of the vertical. So it can only see a narrow swath of the sky. I mean, it sweeps out, you know, 360 degrees per day, but it could only go down to about the equator and up to about 40 degrees north declination. So it can only see a fraction of the sky.
Wow. So it's a good thing the Earth really is rotating.
Yes, it is. Yeah. And it just so happened ISE 3 was going through, was in that declination range, and that it was visible in the dish during a time of day they were doing maintenance. And they had a staff there that was really excited about volunteering their time to help out. So that was a once in a, you know, all the stars came together for that one. I always wonder what those antennas are at the bottom of the dish. What are those, radar transmitting antennas? What are those?
I have no idea. You know, the with the angle they're on, I was going to say it could be that they were just going to communicate straight up, but if they're those magical dipoles, that's the hole in the donut.
Well, I don't know. I mean, the focus of the dish is up where the feed point is.
Well, yeah.
Remember, it's also a sphere.
Right,
it doesn't focus. It doesn't focus at one point because it's a sphere, not a paraboloid. That's how it could be steered, or you know, away from the vertical.
Oh, I thought they slid it back and forth on the track.
Well, no. You see how they have that thing can rotate where you get the mouse cursor.
This rotates.
Well, yes, that's azimuth track, and then it can slide along it. Yes. So that allowed them to steer the point at some point other than straight up, but it did not focus on a straight line or a point. It was focused on a line because it's a sphere segment, not a paraboloid. Again, this thing was designed for something other than what it was ended up being. So,
all right. Well, it's 10 minutes till 9. And I guess I don't know whether or not our fearless leader is still there.
Yeah, I just put a link to the video in chat.
Oh, all right.
Oh, to that collapse. Oh God, that was painful.
Yeah, I have limits to what I'm willing to put up on the screen during a meeting.
Yeah.
You know, I was willing to put up the aftermath, but I'm not willing to put up the actually watching it happen.
Well, that'll be up to the individual's discretion to click on the link if they desire.
Yeah.
Yeah, I'm sorry, I can't do that. It still hurts too much.
Yep.
Yeah.
Well, just a wonderful cap on 2020.
Yeah.
All right. Well, Joe, this is the point where you're supposed to ask if there's anything else before you close the meeting.
For the good of the club and everyone, is there anything else before we close the meeting? Not hearing anything. Thank you very much for the presentation and the chit chat and questions. Very informative. Great meeting. Thanks much. Mark, you can go ahead and stop the stream, and we'll see everybody next month. Meeting topic to be determined.